has done, because she has this like crazy wire walker, which is a high frequency profiling thing. She can look at the carbon on a really high, really thin intervals. And she can make this graph on each of these depths. No? And since you have day, night, you can calculate the rate of change for different types of amounts of light. And you start getting something similar to the prime productivity curves. So you can say something about the specific growth rate. The change in the carbon is a function of light. This is usually done analytically in a lab using incubations of carbon and so on. But she managed to do it this way. So this is pretty awesome, because now when you have this, you can apply it back to your wire walk or any kind of data and start talking about something about the change of the rate of carbon, change of the rate of carbon production or respiration and so on. Diatom's important, because not just because what they do when they're alive, but also what they do once they're dead. You know, they export the carbon. This is actually the words that Will Smith said in this documentary. It's called One Strange Rock. It's pretty awesome. I didn't never know that I'm going to hear Will Smith saying diatoms, but he did say that. So we really want to figure out a way to follow these things as they're falling down, like in that video. No. Nathan Briggs, the one that publishes awesome papers, but it takes him a long time. What he did was start looking at the. I'm a co-author in all of them. That's the problem. You're going to keep me here. You know, he's a genius, but he's just a slow genius. I'm not. Anyways, so what Nathan did is he looked at the spikes. We did lots of these profiles in North Atlantic bloom, and these spikes started appearing. So you know, you have your profile backscattering, spike. What are these spikes? So what he did, he ran a median filter. He removed the mean signal away and started looking at the spikes. So again, variability around 1-to-1 line, and start plotting this spike as a function of time. So what he's seen is that as you start getting bloom happening, so this upper plot is the bloom. As you start seeing the increase in scattering in a surface, this is total scattering, you start seeing an increase in the spikes, and they have a function of time. So what he did by using the spikes and scattering and spikes as chlorophyll, he actually managed to follow the export of carbon. Using the conversion rate that I developed from backscattering to carbon, he can actually say how much carbon is exporting. And he can tell you something about velocity, and he can differentiate the carbon, because he did the same thing with chlorophyll, from the sediment plume that was here. No? And that was confirmed because we had a sediment trap down there, and we knew that exports was fast because these guys were almost alive. The stuff was just falling down through the water column and exporting this carbon. Once again, optics. He actually did some more further work in his postdoc, where we started looking at the disaggregation and aggregation processes, the things that Emmanuel started looking. So he once again used that spikes and start filtering these spikes in different way to start looking at the fluxes and disaggregation processes in a water column, which are really important when you start really dwelling down on the amount of carbon that reaches different depths in the ocean. I'm trying to go faster this because it's lunchtime, no? He also did, and he published this, yay. He used I'll shut up. This, 2018. This was 6 years in making. It's an amazing paper because he went and did everything that anybody can do using optics and using oxygen, all these autonomous sensors, and tried to really estimate a great way of saying something about different types of production. So gross production, net primary production, so on, and compare these methods with the scope of North Atlantic bloom. And so what he's seen that he can calculate gross primary production, net primary production using chlorophyll. So the difference is respiration. And then using his spikes, he can calculate exports, no? So he's closing up his carbon budget, no? And then he used the variance to mean ratio and backscattering to see the increase in aggregate formation. So he knows what was the production, what was the respiration, how much carbon was exported, and pretty much he can say something about the size of these aggregates as they're singing through the water column. All done by optics. I think I have optical sediment trap, then we're done. Optical sediment trap this is like, yeah, Meg, she's queen. So what she did is like, kind of like Jim Bishop did that before her, but she took a C-star, your attenuation meter. Instead of measuring it this way, she put it like this. Tied it to the float, I let it float around. So what happens? Remember the video? I'm sorry?
No flow speed, open.
Yeah, open. So remember the video. What happens in a deep ocean? Things fall down. Your aggregates fall down, things happen. So if you deploy a attenuation meter in the ocean like this, what's going to happen? Exactly, particles are going to fall on it. So there you can use your attenuation meter as a sediment trap. You can look at the accumulation of these particles in your optical path, calibrate it, and estimate the carbon export. And Meg has done it, no? So these are just different experiments where she was looking at the carbon flux versus attenuance flux, because she refers to this as an optical sediment trap. And she found relatively good relationship. Of course, there's some uncertainties, which she plotted. So she knows what the certainties are. And when she has that, she can actually try to extend it to her whole data set. So this was a deployment. This is the paper from 2013. She has a great paper from 2019. This is a deployment of one of her floats. And you can see up here chlorophyll fluorescence. And these purple lines here is the export as calculated from that optical sediment trap. No. But in her paper in 2019, she went full on proxies. No. She used chlorophyll to backscattering ratio to look at the community composition. She looked at the backscattering to CP ratio to say something again about particle composition. She did this. She did the spikes. It's awesome. Check it out. Link is here. It's really great. It's like one of these ultimate things on how to use optics to say everything about the carbon, what's happening in the ocean. Okay? Yeah, she will. She's going to probably come and. Yeah, and she took the class with me. So anyways, I spattered through this stuff. This is just different ideas, different things that you can take home. Understandably, you can develop proxies. Proxies will take you only so far, no? Again, Mary Jane Perry, the one with the Mary Jane swirl. Sorry, I'm getting caught again. With the Mary Jane swirl, no? And many other things. And the person who started this class always says the proxies work until they don't, no? And the reason for that is that people very often start extrapolating things outside of the comfortable range. If you develop a proxy, use it within the scales of your project and understand what are the limitations of it, no? Rather interpolate than extrapolate, no? Don't publish stuff with my proxy without using your own data, because if it comes to my table, it's going to be rejected. Think about it, no? And same as Rufus the docs. Use the variability and chaos, and remember 1 and 2, and publish some new proxies so we can use them now. And that's it. But I have to do it. This is my soapbox. Okay, let's do this. These are the mean boys, no? End of the 19th century, beginning of the 20th century, the plankton boys, no? Ernest Haeckel, really famous. I mean, I think everybody heard about Ernest Haeckel. He was like a great zooplankton person, zoologist, who was telling you learn a lot from him about evolution of the zooplankton, just generally zool evolution. Anton Dohrn, really important for zooplankton. Alfred E. Allen with the plankton collector. So he's the one who started the phytoplankton time series in Scripps. If you look at the Scripps Spear, they have phytoplankton data from 1926. It's an amazing thing. What is one thing about this image that we see here? Colin, tell me. Okay, students, what do you see about this image? What is wrong with this picture? Exactly. Look around you now. It's 50-50. So, tomorrow is World Ocean Day. The topic of the World Ocean Day is gender in oceans. And it's important fact, I just have to say, I'm a big fighter for this. It's 30-80% of marine scientists is women. I'm here in everything way I am because of the amazing support of this class. You, and I'm sorry, this is really important for me, you and Mary Jane. Because what this class gave me is a lot. And I don't get usually this, but it means a lot to me. So you guys are going to be a great community. You have us in the background. We're going to, we fought for you. We fought in front of you. We're here for you. Boys take care of the girls take care of the boys. And really, this optics class always does this. It always allows women to step up in a situation where we don't get step up. And people from optics class give you that netting that if you fall, they're going to pick you up, okay? So yeah, go to eat lunch. Sorry about the tears, but this is really important for me. So yeah. Thank God it doesn't look this way anymore. Can you imagine going to field and with the tie? Okay, if you have questions, ask me later, okay? Go eat lunch.